Hello students, in this lecture we continue with the root locus. Now in the previous lecture of root locus we have taken an example of this transfer function, open loop transfer function, that is k upon s plus 1, s plus 2 and s plus 3, and we plotted a root locus for this particular system which was represented by this graph. Clear? Now moving further, now suppose we have given a certain point that let's suppose if this point is given to us, that is s is equal to minus 0.75 plus 1.5 I. Now we need to check whether this point really lie on this root locus or not. That is, if this point does this point lie on this root locus, or can we, or the other way is this point is a part of this root locus. Now this is to be checked using the next rule, that is the 8th rule, which is angle criteria and magnitude criteria, angle criteria and magnitude criteria. That's the next rule, where we, in this rule what we do is we basically check whether the given point is a part of root locus or not, and that is by using this angle criteria and magnitude criteria. Now what we do is, let's again, I'll again plot this thing on a very different, neatly again. Let's suppose this is 0, this is minus 1, minus 2, and somewhere here this is minus 3, and we had 1, 2 and 3, yep, 3 poles over here. So we have 1 pole over here, 1 pole over here and 1 pole over here. Now let's suppose, and this is 1, 2 and 3, that's minus 1, minus 2. Okay, now suppose this point is somewhere here. Clear? Let's say this is that point S. Now we need to check whether this point lie on the root locus or not. Now for this we use angle criteria rule. Now angle criteria says, what we do is we join this point with all the number of zeros and poles. We join this with all the number of zeros and poles. So that means using a scale we'll join these points. Okay, my mistake, I've made it wrong. This has to be done using a scale. Clear? So we connect all these points with that given particular point with the help of a scale. Now once we join all these points, what we do is we measure this theta 1, we'll measure this theta 2, and we measure this theta 3. We'll measure all these angles. Clear? So that means theta 1 plus theta 2 plus theta 3, these are from the poles, minus phi 1, phi 2, phi 3 from zeros. If suppose there is some zero, currently there is no zero, so this term will be 0. So if there is any zero, suppose if there is any zero somewhere here, suppose it is suppose it is this thing at minus 4, so we need to measure this also. Clear? So that will be your phi 1. Clear? So currently there is no phi, so let's not use it. Clear? So now we measure all these angles. Now angles from all the poles minus angles from all the zeros should come out to be equal to n pi, where n should be a whole number. N should be a whole number. It cannot be like 160, the angles cannot be like 151, 141, 121. It has to be exactly 180, 360, multiples of 180. Clear? Now I have measured these angles. You can also measure it properly with using your graph paper and the D protector. Now theta 1 comes out to be 81, theta 2 comes out to be 51, and theta 3 comes out to be 34. Now if we're going to add all these angles, the angles comes out to be 166. So since 166 is not equal to n pi, where n has to be a whole number, So that means this is not the point which lie on the root locus. Simple. So that means this point doesn't lie on the root locus. Clear? Now suppose instead of this, let's take another point s equal to minus 0.95 plus 1.5 iota. We just shifted by shifted towards more towards the left hand side. Now I've taken this point. Now let's again try this point, whether this point lie on that or not. So again, minus 1, minus 2, minus 3, minus 1, oh sorry, 1, 2. So somewhere here, let's say this is that point, that minus 0.95 and this. Now we'll again measure this angles. We'll join it with, we have a pose over here, so we'll join these angles. So let's say theta 1, theta 2, theta 3. Now measure angle theta 1, theta 2, theta 3. I have already done. Theta 1 comes out to be 88, theta 2 comes out to be 56, theta 3 comes out to be 36. If you're gonna add up, it's gonna come up to be 180 by n, s equal to n pi, where n is equal to 1. So that means this angle lie on the root locus. So that means this point is somewhere here. That is, this point is somewhere here. Clear? So we can identify multiple points. We can identify multiple points, and then once we join this, we have the perfect shape. So that becomes quite tedious. So that's why in the root locus segment I said we have 3 points, one point over here, the other one, simply join it, you have your shape. So this is how you identify that this point lie on the root locus. So this is the point where it lie on the root locus. Now since this point lie on the root locus, that means it must be having a gain value, k value between minimum and maximum. So we need to now identify that k value. Since this point lie, yes, we can say yes, it lie on the root locus. So we need to identify the value of k. Clear? Now how to identify that value? For this, with the help of your scale, with the help of the scale, we're going to measure this distance. With the help of a scale, measure this distance, measure this distance, and measure this distance. So let's say s minus from point 1, that is from this point, the distance is 1.5 centimeter. S minus p2, the distance is 1.82 centimeter. S minus p3, the distance is 2.52 centimeters. Clear? So we measured these distances with the help of a scale. Now if you look back at your open loop transfer function, it was k upon s plus p1, s minus p1, s minus p2, s minus p3. That was this thing, that is k upon s plus 1, s plus 2, s plus 3. Yes or no? So what we do is, for value of k, the mod of s minus p1 into mod of s minus p2 mod of s minus p3. We're gonna put the distances which we have measured over here in this equation, equal to, this is equal to 1. So k upon, what is s plus s minus p1, it was 1.5, p2 1.82 into 2.52 equal to 1. So k comes out to be 6.88. So the k value which we said over here should be between 0.286 and 60. Yes, the value is 6.8. That means over here at this particular point, we have s is equal to minus 0.95 plus 1.5 iota. This point lie on the root locus and the value of k is 6.88. Clear? So this is your magnitude criteria. Now suppose if there is any pole over here, if there is any 0, sorry, suppose this is the 0, minus 4. So we measure this distance. So what will be, let's say, s minus z1 somewhere around 3.5 centimeters. So in this equation, so we're going to have that s plus 4. So let's say that is s minus z1. So that will be 3 point, how much is distance? 3.5. Yep, 3.5 centimeter. So we have 3.5 centimeters, so it will be divided by 3.5. So k is something nearly about 1.5 something. Clear? So this is how you can measure the distance of that particular point from the pole and from zeros, and then you can use in your main expression of your transfer function and calculate the parameter value k. So this method is known as the magnitude criteria. Angle criteria, we identify the point whether it lie on that root locus or not. Once it's proved, then we apply magnitude criteria to calculate the value of the gain. Clear? So this is all about angle criteria and magnitude criteria. Moving further, now there is something interesting regarding root locus. Now suppose we have a root locus something like I have a root locus something like k into s plus 1 whole square over s plus 2 whole square. Let's plot the root locus for this thing. Clear? So n is equal to 2 at minus 2 and minus 2, m is equal to 2 at minus 1 minus 1. Clear? So root locus is valid for n greater than or equal to m. So there are two numbers, so yes, it is properly valid. So let's say this is minus 1 minus 2. So we have two zeros at minus 1. So one zero is this, the other one is again 0. So we're gonna highlight it a bit bigger one. Minus 2, we have two poles. So we have one pole, we have another pole. Clear? So we have two poles. Segment. This section, okay, loci, number of loci, 2. It should lie on the segment. Let's see. First, is this a segment? No. Is this a segment? No. Because while saying we need to treat, now there are two zeros over here, so we'll be treating as 2. Clear? So there are two zeros, so they're even in number. This part 4. So that means on this entire axis we do not have any segment. So we do not have any segment. Second, number of asymptotes, n minus m, 0. So there won't be any asymptotes. So there is no asymptote. Number of loci, loci should originate from the poles. Now there are two poles, so obviously two zeros. So both start from here and they will move towards their respective zeros. So one moves from this side, the other moves from this side. There is no breakaway point. So this is somewhat a special case where you do not have any segment, where you do not have any asymptotes, where you do not have any breakaway point, but you need to show the root locus. So that is this thing. Clear? Now the important part over here is you need to remember, if there are two poles at a same point, it is to be treated as 2. If there are two zeros at a same point, it is to be treated as 2. Clear? Now let's take another example. Plot the root locus for the transfer function k upon s into s plus 1 s plus 2. Very simple. First, n is equal to 3 at 0 minus 1 minus 2, m is equal to 0, so there is nothing. Number of loci equal to 3 at 0. Okay, number of loci are 3. Okay, because it's equal to n. Third part, root locus segment. Root locus segment we need to plot. Now for that, let's take a graph. -1, -2, -3, -4, 1, 2, 3, 0. Now poles 3. So let's designate by cross sign. One is over here, one is over here, and one is over here. Segments. So this will be a part of a segment because on the left hand side we have odd number, on the right hand side we have odd number, this won't be, and then we have this thing. So segment is between 0, -1 and -2 to -infinity. Clear? Now fourth point, asymptotes 3 at center of gravity 0, -1, -2 over n minus m, 3 at -1. So -1 angles pi by 3, pi and pi by 3. So okay, so one angle is this, the other angle is somewhere here, and the third angle. Clear? Since the asymptote cuts the imaginary axis, so root locus will also move towards this thing. Now remember one thing over here, I haven't discussed over here. Now root locus cannot, remember root locus cannot cross the asymptotes. Remember this thing, root locus can never cross the asymptotes. Clear? Now moving further with the example. Now since the asymptotes are cutting the imaginary axis, we need to find out the point at which, but before that, well, let's find out the breakaway point. Now breakaway point is, this was rule number 4, 5, okay, fifth breakaway point. Now breakaway point is 1 over s plus 1 over s plus 1 plus 1 over s plus 2 equal to 0. We'll have a simple quadratic equation, solve it. We'll have two values of s, one is -0.423 and the other is -1.57. Let's see, -1.57 doesn't lie on this, so hence this is neglected, and that's your breakaway point. So somewhere here is your breakaway point, that is 0.421. Now point at which root locus cuts the imaginary axis. Point at which root locus cuts the imaginary axis. Now that will be determined by characteristic equation. That is the characteristic equation. The characteristic equation is s into s plus 1 into s plus 2 plus k equal to 0. So it becomes s cube plus 3s square plus 2s plus k equal to 0. We prepare an array 1, 2, 3, 4, 1, 2, 3, k, 6 minus k over 3 and k. So this positive, so k is equal to 6, so k has to be 6. Now point at which this cuts, so put this value over here, put s equal to iota a, find out the value of a, so a comes out to be plus minus root 2. So that means the points are, one is over here, the other one is over here, so we're going to join this, so that's our root locus. Clear? Now maximum value of k is 6, least value, if we put s equal to if we put s equal to this value over here and calculate k, put s equal to minus 0.42 in this equation and calculate k comes out to be 0.385. So that means for a system to be stable, 0.385 less than equal to k equal to 6. That means for this root locus over here, k is minimum, which is 0.38, and over here k is maximum, which is 6. So in between 0.38 to 6 there are infinite values for which the system is stable. Clear? Now There is one more important thing which I need to discuss over here, how to find out the damping coefficient. If you remember, what is damping coefficient? Zeta, which appears over here in the second order system. We can also identify this zeta from the root locus, because from the root locus we can determine the nature of the response, because zeta if zeta is less than 1, it's underdamped, we have an oscillation. If zeta is equal to 1, critically damped, non-oscillatory. If zeta greater than 1, overdamped system. Now how to determine this thing? Now for that, what we do is okay, for this what we do is we know that our transfer function is, let's say, k upon tau square s square plus 2 zeta tau s plus 1. In the denominator term, the roots are minus zeta by tau plus minus under root of 1 minus zeta square by tau iota. Clear? The roots of the denominator are these. Now if we plot these on the imaginary in the complex plane, from this part to this part it is minus zeta by tau, the real part, and from this part to this part, that's your imaginary part, which is under root of 1 minus zeta square by tau. Clear? Now let's suppose in the example over here, in this example we tested that we checked that this point lie on the root locus or not. Clear? Now corresponding to this particular point, we need to find out zeta. Obviously zeta will calculate the point which is lying on the root locus. Now suppose this point is lying on the root locus, we need to find out the damping factor for this. For this, let's say somewhere here is that point, that is minus 0.95 plus 1.5 iota, that point for that example. Clear? Now we're gonna join this point with the center, with the axis, with the at the origin. Clear? Let's say this is phi. We know this part is this. Now what is d? Can we find out the distance d? Distance d will be zeta by tau whole square plus this term 1 minus zeta square by tau whole square under root. Let's find out the distance d. That will be base square plus the perpendicular square. So d comes out to be 1 by tau. So d comes out to be 1 by tau. Now what is cos of phi? Cos of phi is base upon hypotenuse. So base is minus zeta by tau by 1 by tau. So this comes out to be your, obviously we'll gonna take a mod of this. So from here zeta is nothing but cos of phi. Clear? So if we know that this point lie on the root locus, so corresponding to this point, what will be the value of damping factor? That's simple. Join that point with the origin, calculate this angle phi, cos of that phi will be your zeta. So clearly you can see root locus helps us to find out damping factor, it helps us to find out the location of the roots. But the only drawback which it is not able to eliminate is for lag systems. If a system is having a lag, the root locus again fails. Now let's revise. Routh test fails to identify the location of the roots. It fails for the lag systems. Root locus identifies the location of the roots but fails for the lag. Clear? Now this drawback of root locus will be eliminated in the next section, which is frequency analysis or Bode plots. Thank you.